What if I tell you that in less than 10 minutes, you can professionally design a plate and frame heat exchanger using Aspen Exchanger Design and Rating? By the end of this video, you will know exactly how to enter the process data, configure the heat exchanger, select the appropriate design parameters, and obtain a complete thermal and hydraulic design. Whether you are a chemical engineering student, a practicing process engineer, or preparing for industry, this tutorial will guide you through every step without skipping any important details. Let's get started. Hello everyone, welcome back to Chemical Engineering at Aspen channel. I am Dr. Muhammad Haris Humayun, and in today's tutorial, we will learn how to design a plate and frame heat exchanger using Aspen Exchanger Design and Rating, or we can call it as Aspen EDR. Plate and frame heat exchangers are among the most efficient heat exchangers used in modern process industries because they provide excellent heat transfer while occupying much less space than conventional shell and tube heat exchangers. In this tutorial, we will perform the complete design from scratch using Aspen EDR. We will begin by entering the hot and cold streams data, defining the operational conditions, configuring the exchanger geometry, and finally analyzing the design results to ensure that all process requirements are satisfied. As we progress through the tutorial, I will explain not only which values to enter, but also the engineering reasoning behind these. Before we begin, if you are interested in learning Aspen Plus, Aspen HYSYS, Aspen EDR, process simulation, and chemical engineering design, make sure to subscribe to Chemical Engineering and Aspen channel. My goal is to help students, researchers, and industry professionals master process engineering software through practical step-by-step tutorials. So if that sounds useful to you, hit the subscribe button and let's continue learning together. Now for this example, we have a hot stream whose mass flow rate is 34,000 kg per hour, which enters the exchanger at 88 degrees centigrade, operates at 446 kilopascal, and has an allowable pressure drop of 35 kilopascal. While coming to the cold stream, it has a mass flow rate of 22,500 kg per hour, which enters the heat exchanger at 10 degrees centigrade, operates at 446 kilopascal, and leaves at 60 degrees centigrade, and also has an allowable pressure drop of 35 kilopascal. So now let's begin the complete design of the plate and frame heat exchanger, and the system is water. Water means on hot side and on cold side, both the streams are water. So we will click on this new button, we will select plate and we will create it. And now we have to enter the data in this plate and frame heat exchanger. Once it is created, the calculation mode is design. We are selecting the plate material as SS304. In process, we can either define our system over here, or we can go to this problem definition, or we can specify process data over here. So it's up to us. First thing is to select the SI unit, converting it to kg per hour. The hot side mass flow rate is 34,000 kg per hour, while that of the cold side is 22,500 kg per hour. For inlet stream, the hot stream that is at inlet is at 88 degrees centigrade, while the cold stream is from 10 to 60 degrees centigrade. The operating pressure in kilopascal is 446 for both hot stream and cold stream. Once we have specified, we now have to specify the estimated pressure drop for both cases, and the estimated pressure drop, we will keep it the same because we have not been given information about it, but for allowable pressure drop, we have been given the information that it is 35 kilo. And for fouling resistance, we select 0.0009 square meter Kelvin per watt. So now we have specified our entire process stream data over here, and you can see there is no cross here, which means we have specified all our required information. Applications options, these are by default. In heading remarks, if you want to give the information, it's up to you, but it's not necessary. Now going to the hot stream composition, we have to specify that our system is water. So obviously, instead of user specified properties, we select BJAC system here. Then we will search the data bank and we will select water as our component. So add, OK, and the mole fraction. Since weight fraction is selected, so weight fraction is 1 since the system contains only one component. So either you select mole fraction or either you select weight fraction, the answer won't change. And in property method, we select ideal as our property method. In cold stream, again similar arrangement, BJAC, and then searching the data bank, again selecting water, adding it, clicking on OK, and now all the requirements have been fulfilled. So once all the requirements have been fulfilled, and since we are designing, we do not have to specify any geometry. Maybe we can specify material of construction, but it is already given as SS304 once we selected. And in program options, if there are any options available to you, you can specify it, but we are keeping it very simple and we are doing a preliminary design. So clicking on this run to check whether our results are reliable. And as you can see, there is no warning, there is no error, and it has given a note or an information that on hot side there is a heat load of minus 1309.2 kilowatt, which has been successfully transferred to the cold side, which is 1309.2 kilowatt. That means that the cold stream has gone from a temperature of 10 to 60 degrees centigrade, while hot stream has gone from 88 to which temperature we will see it in the results. So in optimization path, you can see that there are 12 cases which have been run, and the case number 2 was found to be the most optimized case. So not only the design has been done, but the most optimized design has been selected by Aspen. Then coming to the recap of design, this is the selected design which has been selected for this system. Going to the API sheet to get the know-how of how this system has progressed. So you can see here that it has gone from the hot side has gone from 88, and this was the unknown temperature. So it is 54.89 degrees centigrade. And the other results like density, specific heat, viscosity, thermal conductivity, surface tension, critical pressure, critical temperature, LMTD, heat transfer area, all the results are available to you. So this is the overall flow sheet, or you can see the API sheet that has been given to you in a complete way. Then going to thermal hydraulic summary in performance, you can see these are the performance parameters. Like if I take the name of heat transfer coefficient, fouling resistance, velocity, wall shear stress, pressure drop, residence volume, residence time, all the information is available to you. So you can go one by one to all these tabs to check the conditions and to check the effects. Then going to this heat transfer, that Prandtl number, Reynolds number, these are given to us for the liquid because it was a liquid system. And then in duty distribution, again, all the information has been given to you. In pressure drop, it has been provided maximum allowable pressure drop, total pressure drop in the system, pod pressure drop, plate pressure drop, frictional pressure drop. All the information has been given to us in methods. We have been used plate method as it was selected earlier. Then going to the geometry, in exchanger geometry, there are number of exchanges are 1, total number of plates are 163, plate pack weight, if we talk about empty pack weight, it is 448 kg, effective surface area is 83.7 square meter, thermal conductivity is given. So all the information is given. If you want to check about the plates, the plate thickness, the plate width, the plate length, it has been provided to us all the information by the Aspen. And similarly for nozzles, there is no information. Heat exchanger geometry, which is very useful for installation, that you can see the stream 1, which is the hot stream, is entering at 88 degrees centigrade, while it is exiting at 54.9 degrees centigrade. Cold stream is entering at 10 degrees centigrade, exiting at 60 degrees centigrade. The effective surface area is 83.72 square meter. Number of passes stream 1 to both sides are 3. Effective channel stream 1 to 81. Number of exchangers are 1. Plate thickness 0.6 millimeter. Compressed plate pitch 4.1 millimeter. Area of each plate is 0.52 square meter. Chevron angle is 45. Material type is SS304 and port diameter is 100 millimeter. You can see the horizontal port center is 260 millimeter, while the plate flow width is 380 millimeter, and the vertical port centers is 1368.4 millimeter. And if you go to the cost, the total cost is $9,397 for this system. And for calculation details, you won't find anything because there is no outside separate discussion here. Once you have selected the shell and tube, then there are different discussions over here. So this is the overall understanding of how we have initially entered and how we have got the results. I hope you now have a clear understanding of how to design a plate and frame heat exchanger using Aspen Exchanger Design and Rating. If this video helped you, please give it a thumbs up. It lets YouTube know that this content is valuable and helps it reach more chemical engineers around the world. If you have any questions, and if you would like me to create tutorials on another Aspen software module or a specific chemical engineering topic, let me know in the comments. I read every comment, and many of my future videos are based on your suggestions. Do not forget to subscribe to Chemical Engineering and Aspen channel and turn on the notifications bell so you never miss upcoming tutorials on Aspen Plus, Aspen HYSYS, Aspen EDR, process simulation, equipment design, optimization, and chemical engineering concepts. Thank you for watching, and I will see you in the next video.